Welcome to breadboarding. In the previous video, what we did is got the floppy disk controller wired up, plugged into floppy disk drive and the rest of the breadboard PC, and we tried to actually start up an early version of MS-DOS 330. Now I had some problems there, and it's been a number of weeks since that video, been away travelling, and it's also taken a while to get to the bottom of some of the problems here. Now if you want to look at that video, then there will be a link at the top of the screen up here. And you'll be able to see from the chapters here, we covered quite a lot of the background to floppy disks, some of the designs, in particular Scott Baker's design, how to eliminate direct memory access and to use programmed I/O, and we're going to carry on where we left off. So this is video 19 in the Breadboard PC 8088 version 2 series, and this is part 2 of the floppy disk controller. In order to get to the bottom of this, what I thought I'd do is resurrect the Breadboard PC version 1 and actually put the logic analyzers on the various components and actually see what correctly operating MS-DOS looks like from the low-level signals. But in order to do that, we first of all need to have a quick look at the background to what actually happens when we actually try to start up MS-DOS and to boot any operating system off a floppy disk drive. So the PC boot process, the BIOS in fact does a software interrupt 19 to boot the operating system, and on the XI8088 BIOS that we're using, this actually does a jump to the initial program load section of code, which we'll look at in a second. So this is the IPL code in the XI8088 BIOS, and you can see here that we do floppy disk resets. There are some power on self-test codes you'll see here. So in the power on self-test port output that I record, a lot of these D0, D1, D2 come from the debug information that I've actually put into the startup code here. And we can see here that after resetting the floppy disk controller, we get some parameters related to the running of the floppy disk. Then we try and read one sector from head 0, drive 0, and we try and load that to the memory location starting at 7C00, and that's just one sector, 512 bytes. And then if that's successful, we check the boot signature. So the boot signature are 2 bytes at the end of the sector. So we check to see that the 55AA bytes are there, and we have to be careful in that we know that the least significant byte comes first and the most significant byte comes second when we look at this. And then if that is successful, then in fact the BIOS jumps to execute the code starting at 7C00, which is a code at the beginning of the boot sector. And if it fails, we actually get this boot failed message. And if we just have a look at what that is, so you can see here, boot failed, press any key to try again. This is actually generated by the BIOS. So any message we get other than this boot failed, press any key to try again will actually be coming from the early stages of booting MS-DOS. So that's just something we need to remember. So the key thing really about the floppy disk system, it's pretty unreliable, and in fact the floppy disk boot attempts 4 times before it actually fails, and you'll find in a number of areas of accessing the floppy disks, and generally you need to retry 3 or 4 times because they're not the world's most reliable things, as I've been finding out. So down here we can see that we've got 3 main floppy disk controller interrupts. So the reset the disk system, get the drive parameters, and then do the read of one sector. So that's what we're going to be looking at. And I should also note that the floppy disk boot record is different from a hard disk's master boot record. So if you're comparing floppy disks with hard disks, then there is quite a difference in what goes on there. Now, the Breadboard PC memory map is worthwhile understanding a little bit, because where the various bits of operating system are located and bits of the BIOS is actually quite confusing. Now the main system RAM goes all the way from 0000 at the beginning here, all the way up to 9FFFF. So that's our 640K of system RAM. Above that we've got our CGA video memory. We have the 32K BIOS and monitor EPROM at the very top, so that goes from F8000 all the way up to 5Fs there. And in fact, when the 8088 or 8086 processor comes out of reset, it actually looks to execute the code starting at FFFF0. So that's the reason why we tend to need to always have the BIOS or monitor EPROM at the top of the 8088, 8086 memory. Now, lower down here, the first 1K of RAM is actually used for interrupt vectors, whether it be hardware interrupts or software interrupts. And in fact, the BIOS also uses the top area of this, so it goes from 400 downwards, actually uses that as the stack for when we're calling procedures. Then we need some stack, so it actually makes use of the 256 bytes working down from 400. Now, the BIOS data area is where a lot of the BIOS information is recorded, and in particular, a lot of the status information and configuration information about the floppy disk drives actually goes in this BIOS data area. Now, this generally is in 400 up to 4FFF, and quite often the data segment is always set at the 400 range, and so you'll quite often only see the last two digits of the byte being used for the BIOS data area. Now, when our floppy disk bootloader is loaded by the BIOS into RAM, it's loaded in at 7C00, and in fact that's where we saw there we execute it. And what that will then do is the floppy disk bootloader will then try and load io.sys into 700 to this higher range here. It also loads the root directory off the floppy disk and puts that at 500. And then once the bootloader has actually tried to execute io.sys, then io.sys will then start DOS, and that will then load msdos.sys, and that will be loaded from 8000 upwards. So this is what's necessary to work in order for MS-DOS to start up, and so you can see there's quite a few moving parts, but the key thing really is getting the boot sector from 7C00 working first. So just take a quick look at the floppy disk boot record so we know what we're actually looking for. So there's a lot of information here about the floppy disk boot record. The URL here, the Starman PC Ministry, has a lot of good information about boot records. And I've referred back to this, and you'll see the colours that are here for this MS-DOS 5 floppy disk boot record I've actually reproduced, and a lot of the comments and things on here I've gone through and annotated the MS-DOS 330 version actually in a similar way, so thanks for that. This is what the boot sector actually looks like if we look at it in Norton Utilities. And in fact, the key thing really here is the first couple of bytes, EB3490, and the last couple of bytes, 55AA, that's the magic numbers that indicate a valid boot sector. These are the things we'll be looking for when we're actually going in and looking at the data being read off the floppy disk. So unless we get these first couple of bytes here and these last couple of bytes here being loaded in the correct locations, we don't really stand much of a chance. And we can also see there's some of the text here, so we can see this is MS-DOS 3.3. And also down the bottom, we can also see that there's the io.sys file name and the msdos.sys file name and some of the error messages. Now, these error messages here are probably easier to see on the next slide, but if we get the error messages coming out of here, then we know that this is actually coming from the boot sector and not the BIOS. Now, this is the version of the MS-DOS 330 floppy disk boot sector in a similar format to what the Starman site shows. And the key things really here is these first couple of instructions here actually jump to the beginning of the code that starts here. So the code is actually in green here. The yellow here is just the label for the operating system, so different operating systems could put different information in here. The BIOS parameter block is quite confusing, and that this contains some of the key parameters needed to access the floppy disk drive. This gets updated and overwritten and moved around the place, so this is can be a bit confusing. The main boot sector code here starts here. FA generally is the instruction for disable interrupts. I can also see down here we've got the error messages and also the two root directory file names that MS-DOS requires in order to be able to boot. And finally down here, the two magic bytes, the 55AA, which we use to check the boot signature. So now what I'm going to do is to go into the original Breadboard PC version 1. I've actually put the various logic analyzers on the data bus, the address bus, on the floppy disk controller pins, and also the power on self-test port. So what I'm going to do now is to fire that up. I'll record the logic analyzer signals and we'll have a look at what a correctly operating MS-DOS system looks like when it accesses the floppy disks. You should hear the BIOS power on sound there, and in the background the floppy disk drive's doing quite a lot of chuntering around as it actually tries to load the initial boot sector, probably retrying a number of times I suspect. And then we've got the operating system up there, and we'll just do version just to prove what version we've got. So that's booted, so we just need to have a look now at the recorded logic analyzer signals. Okay, so let's look at the logic analyzer output. So this is the main one. This is the 32 signal logic analyzer I've got, and what we've got up here is the main address lines. So only really looking at the bottom 15 address lines. Then we got the data bus, then the memory read, memory write. There's the IO read and IO write, the floppy disk controller chip select. So that will indicate if we're accessing any of the floppy disk related chip enables. And what I have done is annotated with these timing markers where the key areas of the boot process is. This is then the floppy disk signal. So you can see down here I've got the floppy disk cable, pin number and the actual signal here. So you can see that some of the important ones, things like the index, shows when the floppy disk rotates and there's a hole in the floppy disk. So you should see this probably give a signal about 5 times a second. And the track 0 indicator indicates when the floppy disk is on the outer track or track 0. And then the read data is the MFM encoded data, so we can't really make much sense of that using this logic analyzer. And then the power on self-test port output, this actually shows the postcode, so we can see the postcodes going down here. 0 means trying to boot the operating system. And then the D0, D1, D2, these are my debug messages. EE indicates the disk parameters being sent to the drive for seeks. And then we can see all the way down here, there are actually quite a lot of individual disk requests as the operating system actually boots up. So it is possible to go through and analyse all of that and sort of see which side, which sector, etc. is being loaded. But in general, we only need to do that if we were trying to work out why the operating system wasn't loading properly. So the one we're going to focus on is the data bus and address bus and all the I/O signals. And what I did do as part of this, it's quite a forensic sort of activity. What I've actually done is created a document as I was going through things. So this indicates where the various BIOS data area addresses are for where calibration status of the drives are, the motor status. There's also timers maintained for turning the drive motors off. There's various other status values. The media descriptor bytes are all related to how it actually determines whether or not it's talking to different density and size floppy disk drives. And this basically is an analysis I did over a number of days from the initial program load, but the BIOS going through all the various routines where they were calling various things, sending things out to the various registers. In the past, where I was putting the various markers from the logic analyzer, these are slightly out of date. Basically, this covers the entire process going all the way through reading the first boot sector. And in fact, there's a couple of areas where there's things like reading the IDE markers off the disk. This is how it actually works out what type of disk it is. So this was an area that took quite a bit of time to get to the bottom of. Needless to say, it's quite complicated, but I'm just going to go through the top line headlines really of what we need to worry about when we're looking down here. So to start with, if we actually look at the beginning here, what we can see if this period from A1 to A2, you can see here that the floppy disk controller chip select for the 3F2 is in fact the drive operations register. And what this is actually doing here is this is actually starting the reset of the floppy disk controller by setting bit 2, or the value 4. This is cleared to 0, though we start the reset. We then wait for a couple of clock ticks. And then we set it back to 4, which actually re-enables it. We're then checking the status value. So we have to check the status value of the main status register on the floppy disk controller to make sure it's ready to send data. Generally when it's 80, then it's ready for us to interact with the controller, and there'll be different values when it's actually got data available for us. So then the first thing that we have to do is send a specify command. So the specify command is 03, and then there's a couple of bytes we have to send after it, and this is related to various timing parameters to do with the floppy disk drive, to do with things like head settle times and things like that. And then in particular, this particular byte here has the non-DMA bit set. So normally most PCs, this would be 02, but because we're disabling DMA for our programmed I/O here, then in fact this bit is actually got set. And the last bit in this section is what we actually do is turn on drive motor for drive A. So that's the lowest bit of the top nibble there, so that'll be bit 4. So by setting that on, that actually turns on the drive motor. Now you have to wait for at least about a second or so before the drive motor will have spun up. And so what you'll then see as we zoom out here, this is the waiting, the polling of the timers to wait until we're up to about a second. So now, after about a second or so, we're then into the next stage. Now, in fact, there was a bug actually in the BIOS that I detected that this is actually the second time I ran this on the version 1 Breadboard PC. The first time it didn't actually do this check, and I'll explain the reason why in a few minutes. But this is basically checking to see if the drive status, disk change status has changed. Now in version 1 this is all disabled anyway, so it won't actually result in anything, but it is actually accessing that register to see if the disk status has changed. Then we do operational command 7, and this is a recalibrate, and what this should do is actually tell the floppy disk head to go back to track 0. So this is the outer track, and that should then actually result in the track 0 signal going low as well. And what it will do is set the direction and set the steps, and it will do up to 77 steps until such time as track 0 is recorded. And then after this, what we have to do is a sense interrupt status. So this command 8 is sense interrupt, and we actually have to do this a lot of times. And in fact, we just poll this and we keep on getting a value back. The value at the moment here is 0. And basically, when we get to the end of B, we expect the status to come back of 20, which means the seek has actually succeeded. So what this should mean is that having done the operation 7, this now means that disk should be sat at track 0. And if we go to the floppy disk inputs, we can see that in fact the line here is where the drive motor's been turned on. So you can see motor A is on, it's active low in fact. So when it goes low, then the motor's on and drive A is also selected. And after, see this time, 900 milliseconds or so, we can see that in fact there's been a couple of steps with the direction set, and this should actually cause the head to go to track 0. And we can see the track 0 signal, which again is active low, has then gone low there. A little bit later on, you can see that the direction then changes, and it probably moves to track 1, then probably to track 2, and then here probably moves back. So going back 2 steps back to track 0. So you can see this is the basics of the floppy disk controller output to the floppy disk drive itself. We can see that the various index markers here, so these are typically going to be happening 5 times a second. Since the floppy disk drives rotate about 300 RPM, that's like 5 times a second. And we can also see that as the operating system starts to boot, we're actually reading data off both sides of the double-sided floppy disk there. And the actual received data, this is sort of MFM encoded, which is a variant of Manchester encoding. So, but understanding the encoding of that is beyond the scope of what we're going to be looking at here. So what this indicates is that the calibrate basically gets the head to move to track 0. Then we have to wait for about 45 milliseconds or so. And then the next step, we're actually going to do, what we need to do is to determine what the media is. So it could be that a 1.44 megabyte floppy could have the low density media in it, and so by calling this 4A action, which is read ID, what this tries is actually sees if it can actually read the ID information off the disk for different densities. Now this will be trying the high density 1.44 megabyte form first, and since we've got that type of disk in it, then that should work. We have to poll the status here, so you can see that once we've actually sent the command, it's not ready for any input. The 10 means it's busy, but it isn't ready for talking to it. When it shows 90, it means that it's still busy doing a command, but we can now send some data to it. And in fact, we need to send it the drive number to tell it which drive number we want it to do. And once we send it drive 0, which is drive A, then it'll go off and start. There you can see here that we're then polling the status of that for quite a long time here, until towards the end of the status polling, we see the first bit of data returned. So this is the data port is 20. Now, in fact, if we look at the data sheet for this operation, we can see that the read ID actually returns results similar to other read operations. Gives us the status 0, status 1, status 2, and then the various cylinder head sector information. So in fact, the first 3 bytes will be the status. And if we look at status 0, so status 0 is in fact seek end. So this indicates that the seeking has ended, and then there'll be other parameters and things available that we could see coming after that. So what you'll quite often see when accessing floppy disks like this is that once it's read a parameter, you'll see here that it will write that value to 442, and that 442 is part of the BIOS data area. And if we go back to our Word document, we can in fact see that the floppy disk controller status bytes, so there are up to 7 status bytes returned by the commands. And in fact, from 442, in fact, because this is on this sort of segment here, so it's actually address 442. So we'll actually get the output from the floppy disk controller status here, and there'll also be the last errors at 441. So there's something we can check. Basically what this means is this is the output from the command, and you'll see that there are multiple writes here occurring with the values coming back. Then we actually do the read. And in fact, what we can see here is this is actually the output of the data from the read. So we've actually sent a read command, and what you can see here is that we're receiving a status here to say that there's data ready. We're reading from the data port the value of EB. Now, if you remember, EB was the first data of the boot sector. And in fact, what we can then see is just here, we're then writing EB to 7C00. So this is the first byte of the boot sector. If you look at the next one, we've got 34, and then one after that should be 90. No operation code. And if we go all the way to the end of that, we can see that in fact 7DFF is AA. If we go 1 byte earlier, you can see we've got FE is 55. So that is the last 2 bytes of the boot sector. So it looks like this has read the boot sector successfully. EB3490 and the 55AA. So we've seemed to have read the boot sector correctly. Then in fact what happens is if we look at where we've got 7C00 here, we've got 7C0 when we first load things, but then when we execute things, in fact what we can see here is that this is where the code is actually calling our boot sector. So in fact we can see here 7C00, we've got EB, and if we go back here we can see where the commands are that's actually calling this. So if we see EA 7C00, this is actually the command that's calling it. So that is F94D. So if we go back to the output here of the BIOS, we can see that in fact 945, we have to add 9 onto this to make it F. So that's F945 EA 7C00, and in fact the segment, it's a far jump, is 00. So this indicates that this is where the BIOS is actually called the boot sector. You can see here, this is the call of the BIOS to the boot sector with the lower address 7C00 and the upper address 00 there. So from now onwards, this is the boot sector loading. And in fact, what the boot sector does is that it still calls lots of BIOS routines to actually do this. And then in fact, you can see here that it loads, first of all, the 500. This loads the sector for the root directory. That should have ms-dos.sys and io.sys on it. Then it actually does multiple reads for io.sys. The io.sys is loaded at 700 upwards. And in fact, once io.sys gets executed, it will then actually go off and read all the other stuff. So I think this one here is ms-dos.sys, and ms-dos.sys gets loaded into 0D00 all the way up to 54FF. So if we go back to our memory map, we can see that that is actually what we'd expect. Looks like it is all loaded properly. So this is actually working properly. So I've actually used all that information to compare it against what was happening on the version 2 of the floppy disk PC. So getting back to version 2 of the breadboard PC, I've now got a baseline to actually measure things against. So this was very helpful in the early days. Now I came across a number of problems. So the first one really was that the external I/O PLD I had, which was doing the disk change on read, and the problem there was that both the floppy disk controller and the PLD were actually accessing the data bus during the accessing of the reading of the disk change. So what I had to do is some modifications. So we've got version 3 versus version 2. We now got the LDCR is only enabled for write the floppy disk controller and is enabled for read for disk change. I think basically the floppy disk controller was still outputting stuff in the read even though it didn't support the disk change capability. And also the disk change was actually active low, so I needed to change that to the active low. And then this is just the changing the rules here to only output enable disk change on read, and then to only enable the LDCR going into floppy disk controller on write. So that fixed that particular issue. I also had problems with the active high reset. So the IO decoder actually had something that took in the active low reset and sent it out as a high reset, but it had quite a lot of interference on it. It's one of the problems with PLDs. You can get spikes and things on the outputs. That's what it do is ended up adding a separate Schmidt trigger in a basic inverter gate just to provide a cleaner high reset signal. So that actually caused a number of problems. I also came across a problem with a bug in the BIOS with the floppy disk controller initialization. When I was looking at the version 1, then the first boot didn't really seem to work properly, and then it needed a second boot for things to work. And part of the reason for that was that there was this bug in the BIOS floppy disk initialization, and what it ended up resulting in is, because it wasn't doing disk change detection and it defaulted to 360K mode rather than 1.44 megabyte modes, this resulted in problems. And this is actually the routine to the get drive parameters. Basically, get drive parameters passes in the drive number as DL, but passes back the total number of drives installed on the system in DL as well. And the bug really was here is that the requested drive number was actually being used in some of the routines. So the get media state and set media state was using the value of DL, but in fact, because this had worked out the number of drives, it was updating that DL value too early. And so basically what would happen is all of the media state would end up in the wrong drive. So effectively, rather than drive 0 having the data, it ended up in drive 1. So generally drive 0 should go at 490, but in fact the values were getting put in 491, and that meant that the first time round everything, nothing really worked properly, and so it needed to be corrected. And so this is the change. It's a fairly simple change. We basically save the number of drives in an unused variable there, and we don't actually update the number of drives to the DL value in the caller, which uses the base pointer. And now what we do is we set that number of drives once we've actually called the various get media and set media state. So this meant that the media state was correct, but that took a little while to get to the bottom of, and it was confusing because the version 2 code was not calling the detection of drive change selection the first time through, so that caused the problem there. Next couple of slides show this, so just zoom in. So generally the way how a lot of the parameters are passed into the DOS interrupts is they save the parameters on the stack using the base pointer, and what we can see here is that the value for DL here stored on the stack here is 0, 1, and in fact our media state here, which is 0, 7, which is the high density, rather than being stored at 490, it gets stored at 491. So later, when we actually need to access the media descriptor for drive 0, then we come back as 0 rather than the correct one here, and that turns the drive effectively into a 360K floppy. Just so happens that they don't have drive change detection. And then we can see here later on that when we're trying to read the media type to identify it as a 1.44 megabyte floppy, when we access 490, it comes back as 0. So what in fact happens is where it should be calling the disk change selection code here, it actually jumps over that and skips it the first time through, and that's what was confusing me. I was expecting it to be calling the disk change code, which reads the I/O port at 3F7, and it wasn't doing that. Now this next one was probably the most significant, and there was a similar one down the bottom here. So I was getting errors in fetching the floppy disk controller results at the end of a command, and in particular what was happening is that it would return 7 result codes, but then it would end up trying to read an 8th result code, which would end up with an error. And what appeared to be happening is that it was ignoring the end of command status. Now to cut a long story short, from going back to the original datasheet, then the minimum time from reading or writing data to the status being updated is 12 microseconds, and in fact in this particular case it turned out that we were actually reading the status information in less time than that. So this screen grab here shows that we're during the read ID, which starts at A1, the status changes from the 11 to D0, that indicates that in fact we've got data ready to be read. It's after about 13.4 milliseconds. And we can see here that the read ID that we looked at previously should be returning 1, 2, 3, 4, 5, 6, 7 return results. Now the routine that does this, FDC get results, turn these values until this particular stat busy is clear, or we get more than 7 results and we get an error. And it actually writes the data to that BIOS data area that I've been talking about. So you can see down here that these are the results being actually written to the BIOS data area. Now the problem appears to be that from reading the last bit of data that got saved as that last byte, when we actually go and check the status, we'd expect this status to now say that the command has finished and now we can carry on. But in fact, the time from here to here, if we look over here, is 6.4 microseconds. That is less than the 12 microseconds that we were talking about here. And so what appeared to happen was that it went round the loop one more time, tried to do the 8th result code, which then actually triggered a problem that then raised an error, and then that cascaded all the way up to cause the failure. So in fact, this is the bit of code, the FDC get result. And just to show what we do here, we read the status in at the top here. A little bit later on, after checking various status and things, we read the data in from the data port. And then what we do is we jump round up to here. The only problem is from this reading in the data here, to jumping here to getting up there, this should finish when it gets up here because the stat busy will be cleared. So basically the 90 will go to 80 and it says, oh, I've finished now. And then I can do the jump equal to done. So done would then set the operation as successful and everything goes. So that's what should happen. However, because this is only 6 milliseconds, what happens is that that status hasn't had time from that reading of the data here to change from 90 to 80. So this stat busy has not yet been cleared. And so what then happens, we get down here to try and do the 8th result and it causes failure. So in fact, what I needed to do is add a delay at the bottom here before we go back to here, and that seems to resolve the problem. Finally, this other issue, when reading sector data, occasionally we'd actually get bytes duplicated. So when I was looking at the output, rather than getting 512 bytes back for a sector, I was sometimes getting 513. Obviously, that would mean that the data wouldn't line up and would cause problems. So if you just have a look at what was causing that, it's a similar problem to this FDC results thing in that things are happening too quickly, in which case the status hasn't been updated. So I'll just have a look at some screenshots from the logic analyzer output. So what we can see here is we've read the value 36 from the floppy disk drive, and then we then actually polling the status value here, and it actually says, oh, we've actually got a value ready for you. However, the only problem here is that we haven't actually had a chance to read the next byte yet. It's actually giving the previous byte because this status hasn't been updated yet. And in fact, what happens when we then read the next byte, we get exactly the same value back. And in fact, because of this, this actually duplicates the byte. There aren't 2 36s in the data here, and so that actually ended up with a duplication. And if we look at the data here, we can see that the time F1 to F2, 4.5 microseconds. So what we needed to do is add about 3 no operations, and it just moved this check here about another microsecond, 1.5 microseconds over to the right, which meant that by the time we actually came to read it, then it was saying that there wasn't actually any data there ready. And so by the time we did actually get it, then we'd actually find that the correct data was there. So that actually solved that particular problem as well. Okay, so with those fixes applied, I was able to start up MS-DOS 3.3 and MS-DOS 5. And for a period of time, about 20 minutes or so, everything was working beautifully. Unfortunately, I didn't record any of the video of that. And so since then, I haven't actually been able to get it to boot properly. So if I just show you the messages and things that we're getting at the moment. To get boot failed, press any key to try again. So that comes from the BIOS, so it hasn't managed to load the boot record. But this non-system disk or disk error, this means that this has actually loaded the boot sector and then it has failed. And then closest I've got is this one here where I've got a recording of the logic analyzer signals. It was booting the OS and actually managed to get an awful long way to booting. It was doing many disk accesses, but then it was sort of having to reread a certain section. And that's really the logic analyzer trace I'll be showing you now. Okay, so if you remember earlier on in the video, we looked at this logic analyzer output where we had the MS-DOS 3.3 booting properly. So what I'm going to do now is to have a look at a similar area of the logic analyzer just to see how this compares. You can see here there's blocks where we're loading the boot sector, the root sector, then io.sys and ms-dos.sys, and then the rest of the operating system gets loaded over here. First of all, this is the logic analyzer trace for the floppy disk pins. And you can see here at the beginning here, we do quite a bit of activity, but then what happened then, it kind of got into a problem reading the disk and just went into a loop of resetting the disk, trying to reread the data on the disk. I suspect it's partly due to one of the issues I'm going to show you on this page. So this is the logic analyzer for the address bus and data bus and the various I/O signals. And if we have a quick look at the timing markers here, so the first one here indicates where we're actually loading the boot sector. This is 7C00 and the E8 is the first byte we expect. And then at the end we expect the 55AA. magic bytes that we have for the boot sector. We've got AA, and the previous one is 55. So boot sector is loaded correctly. Then in fact, this one here, B1, this is in fact where the boot sector is then being executed. So this is actually where the boot code is actually starting, and then it actually starts to load the other sectors, such as the root file system sector. This will have the directory entries for io.sys and ms-dos.sys. You can see this is 0500. That appears to load OK. Now this is where it starts to load io.sys, and if we just have a look at the first bytes of io.sys, we expect this to be loading at 700, but in fact it's actually loading at 702. And in fact, if we look a little bit further back here, we can see that there's two other writes to the RAM here. And in fact, this one here is to 700, and the other one, the right here, is 701. So in fact, we've got these stray reads appearing, and this doesn't appear to be that there's actually any data there, because when we actually look at what data is being written here, it's FF, and when we actually look at the read of the disk controller, this is reading FF, and somewhere along here we can see that the status coming here is actually 070, but there seems to be some interference or something going on here. It's actually causing the code to actually think that there is a value here to read. So there's something strange going on to do with the status polling here, either interference or some other reason, which is causing the code to actually read the data from the floppy disk controller when it obviously doesn't have any ready. And then it means that all of the subsequent writes to the disk further on down here are then actually occurring at the wrong point. So this bit here, rather than it ending on an FF, has actually ended on B01. So this is 2 bytes further on from where it should be. So it's no wonder that the operating system isn't loading properly, because due to these odd stray reads that we've got here, we've actually got the bytes are shifted along by a couple of bytes, which is obviously going to cause things to have a problem. And there's a similar issue occurring down here as well. So I need to get to the bottom of why these additional sort of phantom reads are occurring, likely to be related to the reading of the status register in the floppy disk controller. So I'm going to go away and have a look at that, and I'll finish the video here. So in the next video, hopefully we'll have resolved these stray glitches that are actually occurring in reading MS-DOS off the floppy disk, and we'll be able to get the operating system booting cleanly. So thanks for watching. If you don't want to miss out in future videos, please hit subscribe, and if you can hit like as well, just helps to make the videos available to more people.